Good evening, everybody, and a very big welcome to this evening's lecture. We are thrilled to have Professor Dame Jocelyn Bell Burnell to speak with us this evening, and I'll be saying a few words before her talk in a couple of minutes. Before that, if you'd indulge me for a few minutes, I'd just like to say a little bit about the context in which this lecture is being held. My name is Cathy Clark. I'm a co-director at the Institute of Astronomy in Cambridge, and my co-director, Mark Wyatt, is also in the audience tonight. And if you're Cambridge locals, you may be familiar with the Institute of Astronomy because we have well-attended public observing sessions every Wednesday during the dark months of the year. We do a lot of public outreach. But it's a special week for us this week because we are 50 years old as an institution, and we're having a big conference at the Institute gathering 200 astronomers from around the world for a celebration, really, of our history and of our future and of global astronomy. And we're having a wonderful time up there this week. And I think one of the things that's emerged from that conference is a kind of appreciation within our field of the diversity of topics that we study as astronomers. If you just think about the range of size scales involved, some of us look at the tiny objects which may be the platforms for future discoveries of extraterrestrial life, whereas others are focusing on the largest probable scales in the universe. And some of you may have been here for our panel discussion between members of our staff here on Monday, where we were sort of contrasting the views of people who work at these extremes. So I mentioned the word diversity, but there is another kind of diversity that perhaps we should be reflecting on as we're 50 years old, and that is in terms of the diversity of the community that actually does the science. And there's been a lot of changes in that area over the preceding decades. And in fact, we had a public lecture yesterday which was talking about the history of our institute and about the Cambridge Observatory, which preceded it. So I'm talking about 100 years ago, when women were employed literally as computers. They did the calculations, but at that point, all they did was to render the right result, but they didn't have any sort of agency in driving scientific research. And thankfully, we're in a very different position now. I'd just like to sort of emphasize how much it's becoming normalized in the field of astronomy that men and women are driving research and assuming positions of responsibility in the field. And that is something which has changed over the lifetime of the IOA. And so to emphasize this, we've made a little film. If you're interested, you can follow it on YouTube. It's being released in an hour or so on the Cambridge University Astronomy YouTube channel, which is just perspectives of 5 women astronomers at the IOA. We're mainly talking about our research, perhaps a little bit about how the field has changed, but mainly just enthusing about the work we do. And to whet your appetite, I've got a very short trailer for that. It's only going to play for 1 minute, so I will just show you that now and encourage you to take a look.
Most people think that astronomers spend their time looking through telescopes. Now, even though I am working with a lot of astronomical data, I don't do that at all.
What my research is interested in is what happened in the history of our planet that made it the planet it is today and such a hospitable place for humans and life.
Through observing radio photons from produced by hydrogen, we might be able to establish the masses of the very first population of stars, and I think that's very exciting. It's a huge question that is there out in cosmology.
By studying the connection between our theoretical understanding and the data we observe, we can try to piece together a story of the universe.
A young woman thinking of going into astronomy, or people who are making that decision in their teens, encourage them to take a look at it, because what it really wants to convey is that it's kind of normal for women to be working in this area these days, and that is, of course, it should be taken for granted, but it's also something to be celebrated. And before turning to our main item of the evening, I wanted to say one other thing about a remarkable woman who we miss sorely in the Institute of Astronomy. And I'd just like to take a moment to pay tribute to her. This is Rebecca Elson, who, as you can see here, died tragically early at the age of 39, back in 1999, of cancer. She was an extremely good scientist. She was working in the early days of the Hubble Space Telescope, which at the time was as exciting as the James Webb is for us today. But alongside her sort of cutting-edge research, what was remarkable about Becky was that she was a poet, and she was a poet who published her work, and has been described as the foremost astronomical poet of her generation. So I think what is quite interesting about her work, and I do recommend very highly this slim volume of her poetry, is that she reflects about what it's actually like to be working at this sort of scientific interface of knowledge in a cosmic context, the sort of human aspects of that, how we feel as humans while we are grappling with these literally mind-blowing problems. And I'd like, very briefly, just to read you one short poem that she wrote, which I think contrasts very nicely the sort of daily routine of astronomers, which is to do maths and physics and to be delving into data and using algorithms, all that sort of stuff. And the other side of it is that most of us went into this field because we found it just awe-inspiring and inspirational in terms of the enormity of the cosmos. And so the poem is entitled, We Astronomers. We astronomers are nomads, merchants, circus people, all the earth our tent. We are industrious, we breed enthusiasms, honour our responsibility to awe. But the universe has moved a long way off. Sometimes, I confess, starlight seems too sharp, and like the moon, I bend my face to the ground, to the small patch where each foot falls before it falls, and I forget to ask questions and only count things. And I think that we as astronomers do both this. We count things, that's our job, but we do have a responsibility to awe. And as I say, for those of you who are interested in poetry, I think this will make a very interesting read. But now let us turn to the main event of the evening, and the fact that we have Professor Dame Jocelyn Bell Burnell here with us to give a talk, which will be dealing with the origin of the elements and the sort of cosmic underpinnings of our chemistry, our biology, and our very lives. And that promises to be a fascinating exploration. I think her achievements are probably very well known in this audience, but I would just tell you that back in 1967, she made an extraordinary discovery of the first radio pulsar. And I can't emphasize enough how very rare it is for astronomers to actually discover anything which is completely new. And the astonishing thing is that Jocelyn did this while she was still a PhD student. And she helped to build the radio array near Cambridge, which detected the flashes of radiation, which indicated this enigmatic pulsing source. She drew attention to the signal, and she persuaded those around her who were often skeptical of the reality and the fact that it wasn't an instrumental anomaly. And it's well known that when the Nobel Prize for the discovery of the pulsar was awarded, she was not one of the named people, and this has triggered a lot of debate over the years about the whole sort of philosophy of prize giving and what one should do when somebody discovers something right at the very start of their career. I mean, it really is a phenomenal story. But since then, Jocelyn has been so active in so many spheres of influence within the UK and international astronomical community. She's been the president of the Royal Astronomical Society, the president of the Institute of Physics, the chancellor of the University of Dundee. And in addition to that, she has won many prestigious prizes. The Copley Medal from the Royal Society, which is only, I think at the time it was awarded to Jocelyn, it had only been awarded to one woman before, Dorothy Hodgkin. And in the 2018, the Breakthrough Prize for Progress in Fundamental Physics. And very notably, she's put the proceeds, the substantial prize money from that, into a fund to support women, minorities and refugee students from pursuing a research career in physics, which is a wonderful program to have launched. And so without further ado, we're incredibly grateful, Jocelyn, that you're coming to talk to us this evening, and I will let you just take the stage and tell us about the elements. Thank you.
So good evening. Thank you all very much for turning out this evening. I have a very mixed audience. I think my age range is many, many decades. I will work hard to keep everybody on board, so we'll see how we go. So what I'm going to talk about, first of all, is some of the chemical elements, so as you understand what I'm talking about. Then I'll go back to the beginning of the universe and talk about the Big Bang that created the universe some 13 billion years ago. I'll then talk about how stars shine and create some of the chemical elements. I'll talk about star death by explosion, which creates some more chemical elements. And then finally we'll get back to us, how these elements ended up, or some of them, ended up in our bodies. So first of all, a little bit of chemistry, which I trust will be a little bit of revision for some of you. But we'll start with some rather brilliant student answers to questions. Are they right? Which bit is right? So the formula for water is H2O, 2 hydrogens and 1 oxygen atom grouped together to make a water molecule. CO2 is carbon dioxide, 2 oxygen atoms grouped together and combined with a carbon atom to make carbon dioxide. There is a website where some creative student answers to science questions are displayed. It is a USA site, I have to say. But that latter one is really rather clever in its own way. So to get slightly more serious, this is real. This bit's not a joke. This is what we call the periodic table. It's a list of all the chemical elements, and you read it across like you'd read the lines in a book. So you go from hydrogen to helium, you skip back to lithium, beryllium, boron, carbon, da-da-da-da-da, and we're getting to heavier and heavier and heavier chemical elements as we go across and down the table. I had a not very good chemistry teacher at my girls' boarding school, and we asked the chemistry teacher, "Why is this laid out like this?" It was a church school. He said, "God made it so." Well, God may or may not have made it so, but actually there's some physics behind the chemistry here. All the chemical elements in a column have similar chemical properties. So for instance, this lot on the right-hand side are what we call the noble gases: helium, neon, argon. They're gases, elements that are very reluctant to react with anything. We're absolutely fine, thank you, leave us alone, go away. No, we don't want to join a party, go away, leave us alone. Whereas over this side of the table, this column, this lot is highly reactive and is desperate to join with something else or somebody else. And it's all to do with the pattern of electrons in the atom, particularly the electrons on the outside. This column all have one lone electron on the outside of its atom, and that lone electron is desperate for a partner. And so that's a very reactive chemical element that wants to find another appropriate chemical element to deal with. Whereas these ones, the noble gases, have closed shells. There's no space for any more electrons. They don't want to react. They're absolutely fine like they are. And so they stay like they are. And as you read across the table, there's a gradation of the properties. But broadly speaking, all the chemical elements in a column have similar chemical properties because they've got the same structure of electrons on the outside of the atom. Right, well, there's a lot of chemical elements there. I'm not going to deal with all of them tonight, and you wouldn't want me to, because we'd be here till tomorrow morning. So we're going to focus a bit, and we're going to focus on the chemical elements that are in our bodies. And this is where I need contributions from the audience. There's a lot of water in our bodies. Can anybody suggest some chemical elements that you might find in our bodies? Carbon, yes. You won't find carbon in water, but you'll find carbon in our bodies. Oxygen, yep. What's the formula for water? And what's the H? Hydrogen, yep. So we've got hydrogen, oxygen, carbon, good. Iron, iron makes our blood red, yes. Your blood's red, not blue. Red blood, iron in your bloodstream. Sorry, couldn't? Sulfur, yes. Calcium, calcium in our bones, yes. Zinc, okay, let's stop or we'll have the whole periodic table. There are a lot of elements with small amounts in our bodies that are absolutely essential. But we are primarily water, hydrogen and oxygen, carbon because we're organic, calcium in our bones, iron in our bloodstream. And if we deal with a list like that, we have a chance of finishing at a reasonable time tonight. So I'm going to focus on hydrogen, oxygen, carbon, calcium, iron, and the other chemical elements that are present in small amounts. You could probably have got the picture by the time I've dealt with these. Right, I'm a physicist. Do you mind thinking like physicists for a moment? When you were born, you were about this size. You're bigger now. You've got more atoms in your body now. Where have those atoms come from? Any suggestions? Food and drink. Yep. We breathe in and breathe out. That actually changes which chemical elements remain in our bodies and which get breathed out. It doesn't make big change in the number of atoms, number of molecules, but it also means we absorb oxygen and we breathe out more of the carbon. So, right. So food and drink is where we get our atoms from, largely. So maybe we're going to pursue food and drink this evening, maybe. But actually what I'm going to do is pause that story for a moment and take us rather rapidly through the history of the universe so that you can see how the universe's complement of chemicals has changed. And we do know that the universe had a beginning. Everything, it seems, was confined in a tiny, tiny volume. And everything didn't like being confined in a tiny, tiny volume, and so it went whoosh. And this is what astronomers call the Big Bang. And we know that it occurred about 13 billion years ago. And literally, it was everything exploding out from a small volume. Now, it was initially a very hot volume, but as it expands, it cools. Have you felt air coming out of a bicycle tire? It feels quite cold. It's because it's expanding. There's higher pressure in the tire, and the air comes out with a whoosh and expands and cools. So the very early universe was this fireball that was very compressed, and then as things expanded, they cooled. And there was a lot of light, blinding light at the same time. And as that cooled, as everything cooled, some quite exotic particles, small particles formed. And Einstein's famous equation, E equals mc squared, kicked in. Pointer doesn't seem to be pointing anymore. That's interesting. Hardly see it on the screen. The bottom equation, E equals mc squared, that's Einstein. Some of the energy of that initial big whoosh, big bang, turned into matter, stuff, using that equation, E equals mc squared. So a few minutes after this big bang, the temperature has cooled to a mere billion degrees. Actually degrees Kelvin, but with such a large number, it doesn't terribly matter what units you're working in. Far too hot for us. But as it expanded, it cooled more. In the first few minutes, we started to find the centers, the nuclei of some atoms. Hydrogen, which is the simplest atom, and that was the one that was predominant. Some helium, and some heavy hydrogen, which is hydrogen with some extra neutrons in its nucleus. So it behaves like hydrogen, but it's actually a bit heavier. So from a few minutes after the Big Bang, we've got hydrogen and helium. And they've been around for about 14 billion years, which is what we think the age of the universe is. And by billion, I mean 1,000 million, 14,000 million years. But we're not going to make people or plants or planets out of hydrogen and helium. So we've clearly got a bit to go. We've got the first element on our list, and plenty of it, but we still haven't got the others. On this particular slide, if you look from the left to the right, you're going forward in time. Away off to the left was the Big Bang that started the universe, and until about 1 second after the Big Bang, things were too densely packed, too hot, moving around too fast, and if any bigger entities tried to form by things gluing together, they got disrupted. It was a bit like dodgem cars. Everything was colliding with everything else, and you're getting broken back down to the smallest element. But after about 1 second, things have cooled, and temperatures are apparently just right for the first 3 minutes, well, 1 second to 3 minutes after the Big Bang, just right to form the nucleus of hydrogen atoms and then the nucleus of helium atoms. Astronomers can sometimes be whimsical. We call this the Goldilocks effect. How many children in the audience know the story of Goldilocks and the Three Bears? One big child on the front row. Okay. Well, let's all be children. Goldilocks and the Three Bears. You will recall, I'm sure. Goldilocks is out alone one morning for some reason, walking around, comes across this house, which is actually the Three Bears' house. It's empty because the Three Bears have gone out for a morning walk, a bit like Goldilocks. And in the Three Bears' house, there's a table set with 3 places, 3 bowls of porridge, there are 3 chairs, there's 3 beds, and Goldilocks tries Daddy Bear's chair, it's too big. Mummy Bear's chair, too soft, I think was the problem. Baby Bear's chair, just right. She tries their porridge. Something wrong with Daddy Bear's porridge, too hot, I think. Mummy Bear's porridge, a problem. Baby Bear's porridge, just right. And then she tries the beds, and I don't need to tell you, it was Baby Bear's bed that was just right. And if I remember the story correctly, she fell asleep on that bed. So astronomers and physicists have taken over this notion of things being just right. And we refer to the period between 1 second after the Big Bang and 3 minutes after the Big Bang as the period where there was the Goldilocks effect. Things were just right to allow the nucleus of hydrogen atoms and the nucleus of helium atoms to form. It's still too hot for electrons to join them, but we've got the nuclei of the first 2 chemical elements from just 3 minutes after the creation of the universe. After that 3 minutes, everything is whizzing around, and they've got kind of spread out, and there are not many meetings of particles. And the way you make bigger things is by joining things together. But if they never meet, there's no chance for them to join together and make something bigger. So the early universe gave us hydrogen and helium, and nothing else. And because the universe is expanding and cooling, the chance for particles to get together and build something bigger are diminishing. It's not going to happen. Our universe is going to be left with hydrogen and helium, full stop. But it isn't, is it? You're not just hydrogen and helium. So, where did life come from? Where did more chemical elements come from in general? And to explain this, I need to convince you that they've been created inside stars, and I need to talk to you briefly about the birth, life, and death of stars. Stars typically last for millions of years. We won't be here that long. I'll be a bit quicker. So we've got particles milling around. Initially it's just hydrogen, helium. Later on there'll be some other elements and there'll be some dust particles that get formed in the early stars. But initially it's just hydrogen and helium. And these particles mill around, and maybe there's a little random knot where there's a concentration, a little grouping of the particles. And this little group has extra gravity and will pull in another particle or two, which will make the little knot bigger, which will put up its gravity, which will pull in some more particles, which will make the knot bigger and put up its gravity and pull in more particles. And what started as a small random association of just a few nuclei steadily grows and grows and grows. It's got millions of years to do it, and it quite often takes millions of years, but the knot grows. This is part of the Northern Hemisphere sky in the constellation of Orion. It's known as the Horsehead Nebula because of this shape here. It's not actually a horse's head, and it's certainly not a live horse's head. Do you see up in the top half there's lots of stars and some pink gas? This is a very bright star dominating the picture. You see down here there's far, far fewer stars. That's because between us and the more distant stars there's a dark, dense cloud that's cutting out the light from the stars behind it. It's a bit like a curtain drawn across the sky. And we can see the stars that are this side of the curtain, but we can't see through the curtain. Whereas in the upper part there are lots of stars. This pink stuff is hydrogen gas. Hydrogen's very common. So when you see an astronomical photograph with pink, you can say, ha, hydrogen. And you'll be right 99.99% of the time. So this is a bit of the dust cloud that is just sticking up. And because it looks a bit like the head of a horse, it's called the Horsehead Nebula in the constellation of Orion. I think there's one other bit of astronomy that I want to pull out of this. Christmas will be coming. It tends to keep coming round. You'll probably get a Christmas card with a star with a nice little cross through it. a bit like that star, or that star, or that star. This cross shape is caused by the telescope, in the telescope. Did they have telescopes at the time of the birth of Christ? No. So the three wise men would not have seen the star as a nice cross shape. Might be good theology, but it's not good physics. The cross shape invariably is produced by the telescope and in the telescope. It's not actually in the star, attractive though it is. So what I want to concentrate on is some of this darker material in the bottom half of the photograph, because this is where the action in our story is happening. So we got this little random collection of probably hydrogen nuclei. It's got extra gravity, it pulls in more stuff, puts up the gravity, pulls in more stuff, puts up the gravity again, pulls in more stuff. And what started as a random little knot grows and grows and grows until it becomes a really significant ball. And in the middle of this ball, the stuff gets hot and bothered. The temperature goes up. It's being pressed on by all this stuff all around, which is why the temperature goes up. And when the temperature reaches some millions of degrees, nuclear reactions can start. They're called nuclear fusion reactions. And in the center of some of these conglomerations, you can get hydrogen nuclei combining to give helium and energy. And the energy comes out as light. This knot starts shining as a star once it starts these nuclear reactions in its core. And we've got another chemical element, more helium, and we've got the energy that's keeping it shining. The whole process is called nuclear fusion. And virtually every star that you can see is a nuclear fusion reactor. That's how it's producing its light and its heat. So basically what's happening is hydrogen is converting to helium, energy gets released that comes out as light, and in the case of our sun, also a star. And this thing is shining. We have a star. So it's a very simple star, but what has been going on is that 4 hydrogen nuclei, 4 protons, combine to make a helium nucleus. 2 of them has changed color, as you can see, changed their species, but they're basically much the same mass. And this releases energy, and the energy comes out as starlight. And that's what's going on in the sun today, and it's what's going on in virtually every star you can see today. In the case of the sun, it'll continue for about 10 billion years, 10,000 million years. It is, however, using up some stuff, but we'll come back to that. When your star is run out of these red balls, the hydrogen, it can take some of its helium, 3 heliums, and jam them together to form carbon. That releases more energy, and the star can keep shining. So it's sort of second wave of starlight, if you like. And the star will look like this in its early stages. In the middle is where the hydrogen converted to helium, and in the outer layer, it's where helium converts to carbon. So there's the second stage, helium to carbon. So of the elements we need for life, remember this list? Hydrogen, oxygen, carbon, calcium, iron, potassium. Of that list, we've got hydrogen and we've got carbon. But the carbon's locked inside a star. You don't want to be made inside a star, do you? It's too hot. So although carbon exists, it's not yet very available. But it exists. That's a big step. And the sun's life will end at that stage. The sun will go on for many millions of years more, but it will not go on forever. It is using its fuel. one day the sun will run out of fuel. And what we expect to happen is that it will expand and it will engulf quite a few of the planets. It's debatable how many. It will probably engulf Earth. And needless to say, that will be the end of life on Earth. So we're in a one-way street, folks. Make the best of it. You won't get a second shot. But more massive stars have several more laps of the racetrack, if you like, before they quit the scene. And for example, the group of stars that we know are the Pleiades will have several more stages, and big stars like Betelgeuse in the constellation of Orion, it's the one top right in Orion, it's got also several more stages. So quite a few stars will go further, which is perhaps just as well, because we haven't yet got many of the chemical elements that we need for life. We've got hydrogen, we've got carbon, but we haven't, for instance, got iron for our bloodstream. So we need this second lot of stars. So we ended up with carbon in the last stage. This is this table of all the chemical elements, and we were at carbon there. That's as far as it had got. The carbon can do nuclear reactions and make neon, slightly heavier, and sodium and magnesium. And that stage will keep our star shining, because those all release energy, but it'll only keep it shining for 600 years, which isn't a great prospect, to be honest. However, it does give us some of the more chemical elements, which is handy. So we got as far as sodium, magnesium. Neon can convert to oxygen. That does seem like a backward step, but there is some sort of physics logic to it, in fact. And then silicon is built from oxygen. That stage lasts 6 months. That's not very long. You're not going to make a lot of life in that time. So what's going to happen next? Where are we going? And then in one day, the silicon converts to sulfur. The sulfur converts then to argon, and then to calcium. Oh, there's calcium, stuff for our bones. And then on to iron and nickel. So there's iron for our bloodstream. And a late stage star has got lots of layers with the different chemical elements, each in its layer. And it's still shining. That diagram, incidentally, is not to scale. If it was to scale, you couldn't read all the symbols. But we have a problem. We've got elements hydrogen, oxygen, carbon, calcium, iron, potassium, etc. But they're inside a star, in one of these very nice onion layers inside the star. That's no flipping use for us. How do we get it out of the star? The star explodes. Big stars at the end of their lives explode catastrophically, chucking all their stuff out into space, maybe in the explosion making some more chemical elements, and totally destructing themselves, bar the very central 2% of the star or something like that, which might remain. This is a photograph from the southern hemisphere. There's a couple of very visible clouds of gas in the southern hemisphere, first noted by the explorer Magellan. And we call these two gas clouds the Large Magellanic Cloud and the Small Magellanic Cloud. And this is a photograph of the Large Magellanic Cloud. Lots of stars and energy in the middle, so you get this great glow. Then this pink hydrogen around the outside. Millions of other stars, and one picked out with an arrow. Just to be absolutely clear, the arrow's added after the photograph's taken. The universe does not oblige by saying, look at that star, watch it, it's going to do something. That's the star we picked out with an arrow. It has exploded. It was a star that was quite a bit heavier than our sun, been through all that iteration of making chemical elements, run out of things to do, so to speak, shrunk, bounced, and exploded. And there's huge amount of energy in that explosion. The chemical elements that have already been made get spread out into space, and some more get made in the process. Typical explosion like this, 400 million tons of carbon, nearly as many million tons of nitrogen, nearly as many million tons of sulfur, a whole lot of radioactive nickel. It's the radioactivity that will keep the remains of that star shining for several weeks. But these are mostly all spewed out into space. These exploding stars are potentially dangerous. Not only is it a big explosion, but they produce a blast of X-rays and a blast of gamma rays. If one went off close to the Earth, could it be dangerous? Yes, but it depends how close. Betelgeuse in the constellation of Orion, that's the one that's top left on Orion, as we see it in the northern hemisphere. That's the star that we reckon is most likely to explode in this way sometime. There was a panic a year or so ago because it suddenly dimmed. And we thought, is this the precursor to one of these mega explosions? Well, it's still there, so it wasn't. In that instance, what had happened was some cloud had come across between us and it. So a dust cloud out in space, which made the star appear to dim. It's still there, dust clouds passed, it's pretty well back to normal. But it's quite far away, it's 25 light years. Light travels at 186,000 miles per second, and a light year is the distance light would travel in a year going at that speed. It's a large distance, regularly used by astronomers as their yardstick. Betelgeuse is more than 25 light years away, so even if it did explode, it's too far away to be a hazard for us. There are some interesting heavy elements that we haven't talked about, and I'm going to stop the main story for a moment and talk about how we get some of these interesting elements like gold. The way nature has been working is to take an existing nucleus of an atom and glue on another particle or two, and take that one and glue on some more particles, and take that bigger one and glue on, and so on. And you build up the bigger and bigger nuclei. That's fine if everything's stable. But some of the bigger elements are not stable. They're subject to radioactive decay. Radioactive decay is when one of these big nuclei spontaneously splits into two or more smaller ones. And so if you're trying to build bigger nuclei, this is a pain. You've got this dodgy step where it's potentially going to split into two smaller ones, and you're way back where you were last year, and you start building up again, and you get here and explodes, it splits, you're way back down. You know. How do you get past these exploding, unstable elements? I've got an analogy. You're out for a walk one Saturday afternoon, maybe a Sunday afternoon, and your walk involves crossing a river, small stream, small river, and there are stepping stones. And the way you would get across is you step, make sure you're steady, step, whoop, okay, step. But if you come to one that's seriously wobbly, what are you going to do? What are you going to do? Who thinks you fall in the river? One or two. What's the alternative? Sorry? Move quickly. Jump to the next one and hope it's steady and hope you can regain your balance. And that's what nature can do, because the equivalent of the wobbly stepping stone is the latest nucleus you've built is actually unstable and it's liable to go pht. But if you can jump on quickly, you could get past an unstable element. But to get past an unstable element, you need to do 2 jumps very quickly. You need to add 2 things in very rapid succession. So you need a copious supply of particles so as to be able to add 2 quickly, one after the other. Right, you've answered that question very nicely, thank you. You jump to the next stone. And a radioactive element is the equivalent of a wobbly stepping stone. And so the way nature can get past that wobbly stepping stone is to add 2 particles, make 2 jumps quickly, which means you need a copious supply of particles in order to have good chance of adding a second one before that wobbly nucleus disintegrates. And you also have to hope that the next one is stable. If you've got 2 wobblies in a row, you're probably in trouble. So you need lots of particles around so that you could add 2 in rapid succession. And we used to think the place this happened was in one of these exploding stars during the explosion. There's all hell let loose during the explosion. There's all sorts of stuff milling around. And there surely will be a couple of particles that you could add quickly to get past this radioactive element to make the bigger ones beyond it. We're no longer clear that actually there are enough particles around fast enough for long enough to create some of these bigger chemical elements, like gold, like platinum. And we're now thinking we need an even more violent, big explosion to get past some of those bottlenecks. There's a phenomenon we know called gamma ray bursts. Astronomers don't just study light waves and radio waves. We do astronomy in X-rays, in infrared, in ultraviolet, and in gamma rays. And gamma ray astronomers discovered what they call gamma ray burst, a sudden whoosh of gamma rays from somewhere up there. They finally located where. I thought, whoa, that's kind of energetic if you get a burst of gamma rays like that. We'll call it a hypernova. I'm not sure the terminology is sticking, but never mind, it'll do. So it wasn't very clear what was going on. It's possibly the collision of 2 very compact stars behind these so-called hypernovae. That could give us gold, undoubtedly. But whatever it is that gives us gold, it has to be energetic, very short, sharp. And it's probably a catastrophic event. So take care of your gold, folks. Something has got sacrificed in the process. So finally, let's get back to us. I've talked about how these different chemical elements are created. They've somehow got to get here, and they've got to get into us. So there's a big star here, big old star that explodes. Boom! Kicks out a wonderful plethora of chemical elements, kicks out a load of X-rays and gamma rays as well. And some of them percolate over here to where they meet up with another big star. Not originally as big as that one, but thanks to the incoming stuff, getting bigger. And if it's big enough, it can also explode catastrophically and create even more chemical elements and more fundamental energetic particles, some of which trickle over here to where the sun and the planets, including us, are forming. And the sun and the planets are made from the stuff that was here already. Pretty average stuff. but it's joined by some exotic stuff from that explosion, or from that double explosion. And the really interesting elements have come from explosions and joined the stuff that was here originally. And so we owe our chemical diversity, the range of atoms that we have here on Earth, to explosions elsewhere in the universe, as well as the more normal processes that have happened just round here. And if it wasn't for those earlier explosions, typically we've got stuff from 2 explosions joining us. If it wasn't for those earlier explosions, we wouldn't be here. There wouldn't be iron for our bones, for example. Iron for our bones, iron for our bloodstream. There probably wouldn't be calcium for our bones either. So the atoms inside your body, some of them came from the original stuff that was here in this bit of space. But a lot of the important ones have come from exploding stars. On average, 2 exploding stars have contributed to your body. So Big Bang formed some of the chemical elements, the rest are created by stars, but it's the big exploding stars, the dramatic, catastrophic events that have allowed us to exist. And if it wasn't for them, we wouldn't be here. We are very much intimately and ultimately children of the stars. Indeed, you could even argue we are stars. Carl Sandburg from the USA. Remember who you are. Remember you're one of the latest products of millions of years of toil and play and regurgitation of universal forces. The rain and stars and dust of 1,000 worlds that have perished have contributed to the making of you. Thank you very much.
Wonderful. Am I on? I think I'm on. Yeah, Jocelyn, that was so wonderful. Thank you. I think when I was about 8 years old, hearing that we're all made of stars made me want to be an astronomer. So it's amazing to hear that story told so wonderfully. So there are 2 people who are going to be running backwards and forwards with microphones. Does anyone have any questions for Jocelyn?
Or comments?
Questions or comments? Yeah, okay, so we'll start off there, please.
Wait for a microphone a second. It's almost there.
I think I'm loud enough. How do you determine I think back in slide 18, in the beginning, the bracket of 1 second and 3 minutes?
Oh, right, way back at the beginning, yes.
Because some of the numbers, let's say 600, I get maybe how you could measure it or observe it.
Right. But obviously, we weren't there to, make the measurements and observe, which makes it a little bit harder. But it's done by, done by dead reckoning, basically, using the best physics we have, working backwards. And the story seems to hold together in the sense it's consistent, and we haven't managed to prove it wrong yet.
Thank you. So the lady in the blue, if you can reach it.
Hi there. How can you tell or predict if a star is going to explode?
By and large, it's the bigger stars, the more massive ones that explode over about 1.5, 2 times the mass of the sun. So if we can get an estimate of how heavy a star is, we can usually predict what its future path is.
So there's a question down the front. Sorry, I'm making you run up and down the stairs. There's a gentleman here at the front.
When we think of the transportation of these elements across the universe, how can we relate that to our understanding of an element like oxygen, which is gaseous, which in our experience would just disperse rather than be transported in some sort of unit from one part of the universe to another?
In our experience, we're dealing with the whole atom, which is a nucleus plus lots of electrons around it. In the very early physics I'm talking about, we're dealing just with the nucleus, which simplifies it a bit. And although the universe is very large, we have a hell of a lot of time to play with as well. So it's only got to chunter along steadily at a walking speed, and if you're patient, it'll get there.
Yes, please.
Did you find your job hard?
It's a good question, thank you. Sometimes it can be hard. You can be very puzzled. What the heck is going on here? It doesn't make sense. Sometimes that's because you've made a mistake in the arithmetic, which you haven't noticed, but often it's quite hard. But if you put effort in and crack the problem, it's a great feeling when you suddenly realize you've worked it out, you understand it. It's a bit like solving a puzzle.
Down here, if you can make it, Xander.
Thank you for a fascinating lecture, but I feel we're only halfway there. We need another lecture now from an astronomer or biologist of the actual elements, how they do go into the body.
Yes, yeah. But we eat plants and animals. They take up atoms from the earth, so we get some of those atoms into our bodies.
And should we do the lady in pink and then just in front?
You mentioned near the beginning that virtually all stars are fusion reactors. Were you just referring to sort of like late-stage stars like supernovae that are no longer fusing, or are there some other type of stars that don't do fusion reaction?
There are some stars that are too small. They're not actually stars. There are some bodies that are too small, so they the gravity from the material on the outside of them does not make the nucleus hot enough to do the nuclear reactions. So they're tiddly stars, tiddly not stars. They sit there. We know some very faint stars called brown dwarfs, but we've also seen stars die. So we know that there's a number of not functioning stars around. And most of them are very, very light ones.
Yeah, please.
Thank you so much for that lecture, and I really enjoyed it. It reminded me of the importance of having that awe at what we're studying in our science, and I was reflecting on them because I've coming to the end of my third year of natural sciences, and I couldn't help but reflect that there hasn't been enough time in my education throughout my entire childhood to feel that awe at what we're studying in the universe. And so I'm just reflecting on that. I wonder two things. First of all, how can we bring that awe back into our education? And second of all, how can we have science education a bit more with that umph?
Well, looking at the night sky on a clear night is pretty awesome. I don't know that many schools do it, but a number of amateur astronomical societies will occasionally open their telescopes for public viewing. And if you ever get the chance to go to one of those on a clear night, go. It's absolutely stunning. And take the kids, the grandkids, and everybody as well.
I've been a bit biased towards the front. Should we do the person in blue at the back?
Hi, I'm a secondary maths teacher. What advice would you give to my students who are interested in pursuing astronomy, astrophysics? And what advice would you give to me to best support those students?
Right. Well, physics and maths are the two main subjects that astronomers need. Chemistry is interesting, but probably not as essential. Maths and physics are really the main tools of the astronomer today. So you're in a strong position, ma'am.
Excellent. We're almost out of time. Are you happy to do a couple more?
Yes,
couple
indeed.
More
Yes.
Okay, should we have you there, please?
obviously the stars are different colours.
Mhm.
Is that indicated by the elements that are being formed in them?
Yes, that's right. It's the chemistry. Yeah.
And oh yes, please. The other way. Yeah, good reach.
How old is the oldest star living?
Sorry, beg your pardon?
How old is the oldest star living?
Whoa. Well, the universe is some billions of years old, so there could be some stars of that sort of age.
Yes, please.
Hi, thank you for that. Just a trivia question. If the pink is 99.99% hydrogen, what else could it be if it's not hydrogen?
Sorry, did you repeat?
Yeah, so you said when you see images and it's pink or
Oh,
red,
it's pink,
it's almost
yes.
always hydrogen.
Yes. I'm not sure that it actually could be anything else, particularly in an astronomical context. I think the chances of it being anything else that happens to give a reddish flare spectrum is so remote that you're pretty safe saying it's hydrogen.
And should we do the last question in the back?
When you discovered pulsars, what was it about the signal that convinced you that it was a pulsar and not just an anomaly? Was it the intensity of it or anything else?
So this is referring back to when I was a graduate student here in Cambridge. I found a new kind of star called a pulsar. I found 4 of them. If I'd only had one, there would have been very serious questions to ask, both about my ability and what we were looking at. But when you find more than one, and preferably even more than 2, it begins to feel like you've hit the top of a new iceberg, a new population of something. So I was blessed in that I found 4, not just one. And probably finding number 2 was as important as finding number 1 for those same reasons.
I know I said the last question, but I've just seen one more hand and I can't resist. I hope you don't mind, Jocelyn.
The youngest star?
Oh, big voice.
What is the youngest star?
What is the youngest star we know?
Still not here. What is
youngest star?
Oh, what's the youngest star?
Oh, the youngest
Talk about the
star,
oldest
sorry.
stars.
There are stars forming all the time.
How old is the youngest star?
How old is the youngest? Whoa. We work with quite big numbers in astronomy, so it's certainly thousands of years, but I'm not sure I can answer it beyond that. It's a good deal older than you.
Well, maybe that's a good place to finish. Thank you all so much. It's been lovely to hear. Oh.
Thank you very much.